Here's my slides on our lab 4 on oscillations by Michael Bell. So here's our introduction. So as you can see, the purpose of this lab is to observe an example of oscillating motion and spring system. I'm going to create a computer model and compare it to the observed motion. And the main physics principle used in this lab are spring force, Newton's laws, and the energy principle. The law of conservation of energy is a big focus, especially in this lab, which states the total energy in a closed system will remain constant. And here are some of those formulas. Kinetic energy, where kinetic energy is equal to half of mass times velocity squared. We also have our gravitational potential energy, which is equal to just mass times gravitational acceleration times height. And then our elastic potential energy. And as you can see, there's two here, where half of the spring constant times the extension of the spring squared, and then the other one is half of force times that same extension of the spring. So here's my experimental model and tracker. So you can see the initial conditions included the weight of the object, which we assume to be 0.402 kilograms. The object originally starts at rest with gravity potential energy and is released 0 velocity. We assume that the person did not introduce any additional forces. So here you can see that being demonstrated in the tracker. Here's our code. So here we used equations for kinetic and potential energy, as well as velocity and position update. So we calculated the change in energy and the force of spring, and then iteratively calculate and plot the data. So our results. This is the energy graph of the computational model. It shows that the model does satisfy the energy principle. The principle says the total amount of energy in the system remains the same. As gravity energy potential increases in the red, you can see spring energy decreases, which is the green, and vice versa. So the overall energy of the system is preserved throughout the model. Here's a comparison. As we see in the graphs, the computer model in the blue follows the experimental model, which is the red line, closely along the x-axis, but it is also off on the y-axis. This is most likely a result of human error when tracking the experiment's model y position. And below we can see those graphs. So here's our analysis and our source of the error. One possible reason for the discrepancies we notice between the experiment and the model in the y-axis could be a mistake that I made in the tracker. By choosing the bottom of the mass as the tracking point instead of the center, the experimental mass's y position appears to oscillate further down than the model. Also, incorrect estimations for center of mass during tracking process were the sources of the error. So what does this all mean? The total energy seems to remain fairly consistent, satisfying the energy principle. The exposition period estimate is about 2 seconds, and the y position period oscillations is about 1.8 seconds. You can see this in the graph to the right. The y position estimate is less reliable due to irregularities, and this means the fundamental nature of repeating motion is the same. So yeah, you can see this in the right in the graph, where delta k is blue, and that's penis. Delta k or delta u grav is the red, and the u spring or the change in u spring is the green, And also the change in E is the orange.